Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for BSc Honours Physics students. We have been going through a series of lectures on interference and later on interferometers. Especially we have been focusing our attention on Michelson's interferometer, seeing how the wavelength of a monochromatic source can be determined, as well as the wavelength difference between 2 light sources, the refractive index of a medium. All these things can be determined. We now move on to the standardization of meter. You all know that meter is defined or kept in Paris in France. I mentioned about Charles de Guillaume, who got the Nobel Prize, who was the director of Standards and Bureau. And in this lecture 25, the contents will be as follows: measurement of distances using Michelson's interferometer, recap of some of the important points such as division of wavefront, amplitude, path difference, extended source, fringes of equal inclination, white light fringes, formation of circular and straight fringes, standardization of meter using cadmium red line, most recent mercury line having wavelength of 5460.7532 angstrom. And this is the Michelson's interferometer, which we have been discussing for the past 2 lectures. And this interferometer, as I told you, can be used to determine the wavelength of a given light source. When I say the wavelength can be determined, obviously any length is determinable. Any length means a meter can be defined or a meter can be measured using Michelson's interferometer. What is the wavelength of sodium vapor lamp? It is 5893 into 10 to the power of minus 8 of a centimeter. So, if you can measure this much wavelength using the Michelson interferometer, then a meter also should be measurable, can be measured. So, the description of the equipment, other things we have seen in detail earlier. The important point I want to tell is, we have got 2 mirrors. One of them is a fixed mirror, the other is a movable mirror. And when we are talking about the movable mirror, I told you in the last lecture, a movement that has been enforced on mirror M2 by lambda by 4 will lead to a path difference of how much? A movement of mirror M2 either towards the glass plate G1 or away from the glass plate G1, a movement through lambda by 4. It is moved by a distance lambda by 4. Lambda you know in centimeter or whatever we think. So, lambda by 4 movement will lead to a path difference of lambda by 2 because the light travels up and down. So, a movement through lambda by 4 of the mirror will lead to a path difference of lambda by 2. That of course you know, right. Now, I have to see that by lambda by 2 wavelength difference means what? If the wavelength differs by lambda, you know, the condition for the constructed interference will be the path difference should be integral multiple of lambda. So, if the path difference differs by lambda or 2 lambda or 3 lambda, that leads to a bright ring or a bright band. Here we will be talking about circular fringes. In the Michelson's interferometer, you will be coming across circular fringes, and these circular fringes either will disappear or will cross through the crosswire when the movable mirror is moved. I told you in the last lecture, if the mirror is moved through a distance lambda by 4, then darkness you go to brightness. You have a dark region in the field of view. When you see the Michelson interferometer through the telescope, you got the telescope here, you have eye here and look at this particular thing. This is a mirror here and this is a virtual image of the mirror M1. What is M1 prime? M1 prime is the virtual image of the stationary mirror M1. The stationary mirror M1, the virtual image. So, the light coming from or the virtual source and the plane mirror M2, they interfere and they give rise to either darkness or brightness depending upon the path difference. Now, what I want to tell you now, if M1 is equal to M2, that is the path difference is 0, then you know if you have got darkness, right. Supposing you in the field of view you see complete darkness, then how will you get brightness? Brightness will be obtained by when a path difference of lambda by 2 is introduced. From darkness you have a path difference lambda by 2, then you have to go to additional lambda by 2 will lead to lambda, then 3 lambda by 2 darkness, again 2 lambda brightness, and therefore, alternately for every path difference of lambda by 2, there will be brightness, darkness, brightness and so on, right. So, you got darkness here by moving the movable mirror through a distance lambda by 4 or by introducing a path difference lambda by 2, you go from here to here. From darkness, you go to brightness at the center. You got a bright ring here. In reality, the circular fringes that you are getting in the Michelson's interferometer, they will be similar to the Newton's rings which we have seen earlier. You all seen the Newton's rings that you get because of air film. So, similarly, whatever that you got in Newton's rings, you will be having similar rings here, and the rings will disappear depending upon the movement of the mirror, which is possible for us to move. The mirror can be moved. One of the mirrors is stationary, the other can be moved. The other important points which I wanted to bring it back to your memory, the recap consists of the following things. You know, I told you one of the mirrors is fixed, the other can be moved. The other can be moved means by moving the mirror through lambda by 4, it causes a path difference of lambda by 2. So, unlike the case of air wedge or Newton's rings, here the important point is the path difference is easily, keep here this path difference. I am not going to define it again. The path difference between the two light beams which are interfering can be enormously changed by the fact that the mirror can be easily moved. The movable mirror can be easily moved even up to a distance of 10 centimeters. Therefore, enormous path difference or the path difference can be introduced at ease in the Michelson's interferometer. Another point is division of amplitude. There are two methods by which the divisions can be made of the light beam. One is division of wavefront, the other is division of amplitude. In the case of Michelson's interferometer, it belongs to the second class, namely division of amplitude. What do you mean by division of amplitude? The light intensity is split up into two parts. One is a part of the light beam is made to travel through, the other part is reflected goes in this direction. So, the intensity is split up or the amplitude is split up. So, this is a second class, namely it belongs to division of amplitude. The incoming amplitude or the incoming intensity is split up into two parts, one by allowing the light ray to travel through the glass plate, the other is by making the light ray to get reflected, thereby the amplitude is divided. The other thing, as I told you, the ease with which path difference can be introduced between the two interfering beams. And again, you make use of an extended source here. Unlike in the case of Young's double slit experiment, you make use of a point source, but here you have a extended source, and again you are talking about fringes of equal inclination. What do you mean by fringes of equal inclination? As I told you here, you got theta is the angle by which the two light rays make a angle with respect to the eye of the observer. So, the beam, the interference bands make a particular angle of inclination, and so we are talking about fringes which make a particular angle of inclination. So, fringes of equal inclination, and then I have to talk about white light fringes also. Therefore, now here the picture is, I am showing it once again, the one that I showed earlier. You have got a light source here, and M1, M2 are the two, S1, S2 are the two virtual sources, S1 and S2 are the two virtual sources, and the M1, M2 are what? They are the two mirrors. You know M1, M2 by now, you have seen the interferometer number of times, and M1, M2 are the two mirrors. One is fixed, the other is movable. Supposing they are separated by a distance d, this small d, there will be capital, there will be 2d. This small d is the separation. Twice this distance will be the separation between the two virtual sources which give rise to bands. So, the distance that separates the two virtual sources S1 and S2 will be 2d, and that is the reason why I had 2d cos theta, right. 2d cos theta is equal to m plus 1 to lambda by 2. That is what we had as a relation earlier, right. That is the relation that we had for getting the construction bands or the construction fringes, circular fringes to be bright or dark. I mean bright, that means you are constructing your constructive interference condition is 2d cos theta plus lambda by 2 will be equal to m lambda. That is, you had a relation earlier, and the point I want to tell you is the wavelength is a thing that can be measured in terms of the shift in the fringes which are caused by interposing a transparent film. The thickness of the transparent film can be determined, and the lambda is the wavelength of the light beam which is to be measured, and by knowing the value of d. So, the wavelength can be measured. So, d lambda n is the number of fringes that have been shifted, all of the things we have seen already. How will you find, or how will you measure as to how many fringes have been shifted? We will have a short break, and then we will resume with the rest of the things after the break. Welcome back at the break. The essential point I want to tell you with regard to Michelson's interferometer is the following, namely that if one of the mirrors among the two if it could be moved by a distance lambda by 4, it is equivalent to introducing a path difference of lambda by 2. The introduction of a path difference lambda by 2 will make the field of view to go from darkness to brightness, or in other words, as to how many lambda by 2 making, that will tell you how many fringes are disappearing. Fringes are crossing the crosswire, or the fringes disappearing in the field of, from the field of view or the center. So, the essential point is the mirror can be moved. Now, the question that I am asking is whether the mirror can be moved through 1 meter. The reverse, I am putting the question in the following direction. What is the problem before us? The problem is how to define a meter or how to measure a meter. Supposing you can move the mirror through 1 meter, when you are moving through the mirror through 1 meter, how many fringes are collapsing, or how many circular fringes are disappearing? The number of circular fringes that are disappearing should be known. That will give you the wavelength of the, that will give you the wavelength of the source, or the, the meter can be written in terms of how many lambdas. A meter, lambda by 2 gives rise to movement of 1 fringe, or the disappearance of 1 fringe. A movement of 1 meter will lead to disappearance of how many fringes. That is the thing that we have to ask now. And so, in the experiment which was performed by Michelson and Benoit in 1895, and Michelson is a wonderful person in the sense that when he started experiments on his interferometer, many people asked him, why are you doing lot of useless things in the academy where he was teaching? He is the person who measured the velocity of light, and he is again the person who showed that ether is not existing in the universe. Ether is wanted by the wave theory people for the wave to get propagated in space. They wanted a medium. They assumed an ether medium. Michelson disposed of the ether concept. The ether is not present in the universe. That led to the Einstein's special theory of relativity. So, the famous Michelson-Morley experiment, which paved the way for the establishment of the special theory of relativity given by Einstein. So, for the work that Michelson did, he was awarded the Nobel Prize in the year 1907. So, the 1907 Nobel Prize went to Michelson for the wonderful work that he has done in the area of optics, and there are books written by Michelson, original books, which are to be referred to when you want to understand the very many things that Michelson talked about, the visibility of fringes, and then what is meant by a monochromatic source, bandwidth, and so on. There are things that we have to see in the lectures to come. But anyway, as far as this lecture is concerned, the instrumental setup he used would be looking like this. As I told you, the movable mirror, there is a mirror which is to be moved. This has to be moved through 1 meter. Can you move through 1 meter? As I told you in the last lecture also, if any movement that has been done beyond 10 centimeter, the fringes will collapse. The interference pattern will not be appearing at all. So, the path difference should not be too much. Therefore, to circumvent the problem, what was done by Michelson intelligently was to use what are called etalon. An etalon refers to a pair of mirrors. As I told you again in the last lecture, it will be the distance separating a pair of mirrors M1 and M2 will be around 0.3 of a meter, and in the experiment which he conducted for determining or for standardizing 1 meter. Instead of standardizing 1 meter, he made use of substandards. What I mean by substandard is, this distance is 0.3 of a millimeter. Then you have a second echelon. The echelon consists of pair of mirrors. So, in order to do away with the movement of 1 meter, moving the mirror through 1 meter, we are going to finally move from E to F, a few millimeters or few centimeters. So, in order that you don't move the mirror through 1 meter, he introduced as many as 9 echelons. Each echelon will be having a pair of mirrors, and here I am showing one of the echelons, the smallest one, wherein the mirrors are separated by a distance of 0.3 millimeter. The second echelon will have a distance twice the distance. Instead of 0.3, it will have 0.6 of a millimeter. The third one will be having double that, and so on. And he had 9 echelons in total. Final echelon being having the longest distance separating the 2 mirrors. By using as many as 9 echelons, it is equivalent to moving the thing through 1 meter. So, how many fringes disappear is the one that is to be finally seen. Let me now, for the sake of continuity, let me go through the writing that I have here. You know that the construction, working, all these things. Now, I told you about an echelon which is made up of a pair of mirrors, 2 mirrors separated by a distance 0.39 of a millimeter. Then you have the last echelon, wherein the distance separating will be 10 centimeters. You cannot shift the mirror by 1 meter, as I told you. So, the interference patterns will not be formed if the 2 interfering light beams is very large. You cannot move through 1 meter, and so the last echelon, as I told you, I have got distance separating the 2 mirrors by 10 centimeters. So, circular fringes will be visible when you see through the telescope for the instrumental setup that I showed just now. So, circular fringes can be seen, and the movement of the fringes in the last lecture also, when we want to determine the thickness of a thin glass plate, you interpose a thin glass plate in one of the light beams compared to the other light beam, you introduce a path difference, wherein you interpose thin glass plate whose thickness is measured, or you can even have a gas whose refractive index is measured, can be interposed. And the point is, by interposing the thing, the fringes will be moving. The movement of fringes will be yellow in color. The movement of fringes, everything will be yellowish color. The movement cannot be exactly seen. Therefore, what you do is you make use of white light fringes, right? White light fringes will give a central darkness, a central band, a dark band. The central dark band is used to measure the shift cost. That acts as a reference. So, similarly here also the Michelson interferometer, you will be using the yellow light, you will be seeing the colors, you will be seeing the yellow background, as well as you will be using the white light also to find the exact shift or the number of fringes which are disappearing. So, they are all things that one has to see in the literature, passing through again the experimental setup here. And what I finally do is, I am moving the mirror from E to F. When I am moving the mirror from E to F, how many fringes have disappeared, and the mirror M1 is moved, and the number of circular fringes that across the field of view are counted. This is the mirror M1 here that is moved, and the number of fringes that are disappearing or across field of view are counted. For counting that, as I told you, you cannot count it so easily. So, you have to make use of white light. And so, what he did, when white light is used to note the initial and final position of the reference plane P intersecting M1 and M2, whereas cadmium light is used to count the number of fringes. In reality, you have the circular fringes also, and also by making them glass plates to be slightly inclined, you get the straight lines, you get the fringes of this kind from circular rings. When do you get circular rings? When M1 and M2, when the two mirrors are mutually perpendicular to each other, you will be getting circular rings. On the other hand, when the mirrors M1 and M2 are made to be slightly inclined, then you get straight fringes, right? You get straight fringes. Therefore, you will be making use of both circular fringes. How much circular rings have disappeared has to be measured. So, you will be using both monochromatic source, using which you will be getting circular rings. For determination of the number of rings which have disappeared or which are crossing the field of view, any the fringes crossing the field of view is n, that has to be measured using white light. Therefore, you will be using alternately white light. White light is used to determine exactly the number of fringes which are collapsing or which are crossing or moving through the crossfire, because you have a yellow background. So, when a shift is caused, we cannot see the exact shift. So, the shift is measured in terms of the white light fringes. So, suppose the mirror M1 has been moved from E to F. As I told you just now, the mirror M1 is that is a movable mirror. It is moved from E to the position F. The mirror is moved, as I told you here. Suppose the mirror M1 is moved from E to F through a distance L, and N is the fringes which have crossed the field of view. Then, for a length L of the echelon, you know by now what is the echelon and what is the purpose for which echelon is used. I told you in the some time back, the mirror is to be moved through a distance 1 meter, and then 1 meter is the distance which cannot be moved. Therefore, you make use of echelons. So, the final expression goes like L is equal to n lambda by 2. Therefore, the final result with the cadmium red line is 1 meter consists of how much? You can read the numbers 1 followed by 553, 163.5 lambdas. So, the red cadmium line, the red line you have got the wavelength of red line is the following. This multiplied by this is the lambda r, this multiplied by so much number is equal to 1 meter. That is how Michelson defined 1 meter. What is the definition of 1 meter? It is so much multiplied by lambda r, where lambda r is the cadmium red line wavelength. Let me now go to the summary part of the lecture which is delivered now. It goes as follows. As wavelengths which are of the order of 10 to the minus 10 meters can be measured, it should be possible to measure even meters. To introduce large path differences, echelons are used. 1 meter of length will contain so much multiplied by lambda r, where lambda r is the wavelength of red line. The questions are: recall the relation connecting the wavelength of a monochromatic source and the distance through which the movable mirror is shifted. What is an echelon? What is 1 meter? Can it be standardized using any interferometer? If so, explain the procedure to do the same. How many waves of cadmium red line make 1 meter? With this, we come to the end of lecture 25. We see the rest of the things in the lectures to come. Thank you.